Hello friends, in this video I'll be reviewing 1D and 2D kinematics. As for the math review, I suggest you to go ahead and review the notes I uploaded online or your own notes. I'm not going to be doing a specific review about math reviews. However, in the questions and as it comes in the topics, I'll be reminding you about the general applications of math we use. So this lecture will be about 1D, 2D kinematics. As you all remember, we had a 1D motion and we had velocity, acceleration, and distance or displacement we were interested in a certain time. We defined velocity as the distance traveled per unit time, and we defined the acceleration as the change in velocity per unit time. And we were interested in all these variables in 1D kinematics. And again, the motion is along either x-axis or horizontal axis or along either y-axis. Along y-axis we had free fall when some objects are falling down, and along horizontal generally motion generally in life is walking along a straight line or a car driving in a road. First we talk about constant velocity. I'll just remind you the equations and what type of questions we could get. So constant velocity motion, we had only one equation to remember. Its distance is equal to v times t. I'm going to drop the general equation. Usually is distance equal to initial position plus v times t, but we generally start position 0, so we dropped this term. Forgot about it, probably you forgot about it, but actually if there's an initial position that is not 0, we should add that as well, logically. But generally what we have, we start from 0 position because it's a matter of choice. The initial position could always be chosen to be 0. And then, if we know velocity and time, we can find the position of an object after a certain time. And the units here where x is meters, velocity meters per second, and time is second. Generally, as we talked in the beginning, in the math review part, we said we will be using MKS units, generally meaning meter, kilogram, and second. So meter for distance, kilogram for mass, and second for time. Sometimes, however, in some questions, we could be calculating velocity as kilometers per hour or kilometers per minute is all possible, and then we can convert. And if you need a conversion, the values will be given to you. For example, 1 kilometer is equal to 1,000 meters. You will know this and you will be doing conversions if you need to. Similarly, we could have grams and we convert to kilograms, and we said 1 kilogram is equal to 1,000 grams. So this is the only equation we need to know about constant velocity motion. We have a car driving with a constant velocity. We know the time we might pass to find the distance, for example. This simple equation will help us. And then we had a constant acceleration motion. And we had equations. In this case, the velocity will be changing because acceleration by definition is the change of velocity per unit time. So if we have an acceleration, the object is either increasing in speed or decreasing in speed, accelerating or decelerating. And what we said was that we always choose the direction of velocity to be positive in these type of questions. This is the direction. Choice of direction is generally arbitrary. You can choose any direction, but our choice was going to be the direction of velocity. Let's say we have a car, it has an initial velocity with 0, driving the direction to the right, and we say it has a final velocity after some time. And let's say we know the time as well, and we have to find what is the acceleration of the object. If the object is speeding up, then we say it's accelerating actually, and the direction of acceleration is the same as the direction of velocity. And if we always choose the direction of velocity to be positive, A also will be positive. If the object would be slowing down, let's draw this again, my cute car in here again. it still have an initial velocity and a final velocity, what we always choose to call V0 initial and V final. Sometimes books or questions could be referring to initial velocity as VI and final velocity as VF. Just a matter of notation, don't get confused at all. If the object is decelerating this time, so now we have deceleration. Or slowing down, let me say, similar to that one. Slowing down. Then initial velocity will be larger than final velocity. The object is slowing down or decelerating. If we again stick to our decisions of choosing the direction of velocity to be positive, so we're not going to be confusing ourselves ever, the acceleration direction will be now opposite to the motion since the object is decelerating, and the direction of acceleration will be negative. So if the object is speeding up, we'll have positive direction of acceleration, positive direction of velocity, and we always choose the direction of velocity to be positive in this class, we said. And if the object is slowing down or decelerating, acceleration will be opposite to velocity and negative. Let's move on to the equations now and to see what we're doing here. So the velocity will be changing, we'll have a distance traveled as x again, and we assume initial position is still 0. x0 is 0. T0 is 0, so we don't deal with the terms involving these values. Generally, this is the case in this type of college physics courses, so no worries about there, but I want to show it to you to be perfectly scientifically correct. It's important for me. And our equations that we are interested in will be finite initial final velocities, accelerations, x, all could be in a question in time. So the equation that we'll have will be final velocity is equal to initial velocity plus a times t, or final velocity squared is equal to initial velocity squared plus 2 times a times x distance, or we'll have x is equal to 0t, sorry. Initial velocity times the time plus 1 over 2 a t squared. These are the equations for accelerated motion, or speeding up. Let me also remind you about the units for acceleration here. The new value will be meters per second squared. Unit for velocity, if you see here, is what's meters per second. Acceleration is the velocity by time divided by time will be meters per second squared. Now this is for accelerating object. And as we have learned in here, if the object is decelerating, slowing down, we'll be entering the acceleration as negative direction. What will happen is every term involving a will turn into negative. Sometimes in the question we might get confused if we enter the acceleration as negative or not at the end, towards the end of the question. So I choose to tell you and teach you in such a way that we enter the direction of the equations. And at the end, we only talk about the magnitude of acceleration. If we are asked about the direction, we already know the object is decelerating, so the direction of acceleration is negative. If we ever need to show the direction, we will know it's negative already. And in the equation, we don't deal with negativity, just find the magnitude, talk about the magnitude, and change the equations, all these pluses into minuses. Less confusion and helps you give a better and a correct result. So for decelerating objects, what we will have, in a nutshell, is making all these pluses and minuses. So v will be v0 minus at. We put the direction of acceleration here. V squared will be v0 squared minus 2ax, and x will be v0t minus 1 over 2at squared. And we know that the direction is opposite to velocity. That's where these minuses are coming from. If the question is asking us the direction, it is negative. We know that. In the equation, we only play around with the magnitude after we change these pluses into minuses. So this is for decelerating object. This is generally 1D motion. We could have different questions we solved in the midterm review part. On Monday and Wednesday, I'm going to add some more questions involving accelerations, decelerations to practice with these more. And all these equations will also be in your formula page. Now, there was one more 1D motion we were interested in. free fall motion. Everything is the same in the free fall. Acceleration, deceleration, both possible. And only what we do is to replace acceleration with the acceleration due to gravity. And instead of distance traveled to be x, we now call it h. We don't have to, but for height, it makes more sense to call it h. So for free fall, it is also a 1D motion along y-axis, right? Vertical, let me say. And we had different types of free falls we were talking about. First, and the most commonly known one, you drop something down, then zero initial velocity, it will fall down in here. It will be falling down at height h. When it reaches the ground, it will have a final velocity. Initial velocity is zero, we just dropped it, didn't give it a velocity. And the reason for dropping and accelerating down is that we have a gravitational field. Gravitational acceleration always pulling the objects down towards the Earth. We could also make this slightly different, just give it an initial velocity and throw it down with an initial velocity that is not zero now. It will still be falling down, have a final velocity, and still g is the reason why it's falling down. And let's say they both have the same height. We could also throw an object upward direction with an initial velocity. It will go up to some height and come back down, hit the ground with the same initial velocity we throw it upward. This motion will have zero final velocity up here because there will be a moment of stopping there. We will be zero at the highest point it can reach. At any point, this is a symmetric motion. The velocity in the initially first part when it's going up, let's call this V or V1, or let's call it VA, any names we can give, and let's call this point A. As it comes back down the same position on the other side, same level, let's call this point B, the object will have a velocity down. The magnitudes of velocities will be equal to each other in opposite direction, just like in here. This is one characteristics of a motion. And another characteristics, the height it can climb, the highest could be called h maximum. And the time it takes for it to go up and come down are also equal to each other, and we call this t half as half time, the same. And the total time passed can be called t. Total will be 2 times t half. So there are some simpler equations helping us find some values in the fact that the object has the same time value going up and coming down, and at the highest point the velocity is 0. Now let's talk about the equation. Free fall motion has the equations exactly same as 1D kinematics. What we do is replace a by g and x by h, and that's all. Let's write down the equations again in here. The equations for acceleration will be v is equal to v0 plus gt, right? Instead of a, we have g. V squared is equal to v0 squared plus 2gh. If I don't know time, but I know h, I can get to v still. And h is equal to v0 time times t plus 1 over 2 gt squared. This is for accelerated free fall. So the velocity is increasing. So for accelerating objects, that's what we have. If we throw an object upward, the first part of motion will be deceleration. You can imagine that. And the second part of motion will be acceleration. So for deceleration also we must have an equation which will be the same. We again here always consider the direction of velocity to be positive. We stick with this decision. Here downward position will be positive for us, but here the position of initial velocity will be plus. First part of motion and the direction we choose as positive will be changing. Although g is the same, If the object is decelerating, since g is against the velocity, for us it will be negative. And this will take care of the negativity of the acceleration, and we won't be confusing ourselves with mathematical errors by doing that. So what we will do again is, if we have deceleration, instead of plus g, we'll have minus g. Replace plus g with minus g. What will happen? Again, the same. When we take acceleration as negative, all these plus terms will turn into negative. And then we solve our equation, and we know why this negativity is here. The velocity and acceleration are in opposite direction. That's the reason. And the object is decelerating. So for deceleration of decelerating objects, what we have will be the same equations minus in here. Let me write this down for you as well. So we will be v0 minus gt. This would concern the first part of this motion here. Second part, still acceleration. V squared is equal to v0 squared minus 2gh, and h is equal to v0t minus 1 over 2 gt squared. Now, if I look at this first part of the motion, I can use the fact that the object is decelerating. Up here, the final velocity at this top point is 0. I can calculate and I can derive a simple equation for the maximum height these objects can go. I can also derive a simple equation for t half. And I want to show you these equations as well. To derive for the simple equation for t half, so half of the motion. So if I consider this half of the motion, the time will be t half. I have v0, I have v0 in here, and I have time. I can use this equation. V is equal to v0 minus g times t half. And I can derive a nice, simple, useful equation. This will also be given to you in your formula sheet. I have it in front of me here. I'm checking if it's there. Yes, it is there. I'll derive this equation again for you. The v at half point here at top will be 0. So this will go to 0. And I'll end up finding v0 is equal to g times t half. And from here, if I solve for t half will be equal to v0 over g. I can find t half like this. Half time for the whole motion, and the full time t total will be twice that. Simple. 2 times t half will be equal to t total, which means t total is equal to 2 times v0 over g. Now, why is this important? That if I have a motion in this type, turn something up, coming down, I only know v0. Using this simple equation, I can get to t total. Makes my problem solving skills easier. In a similar manner, we can solve for h maximum. Let me take an arrow from here to up there. So still half of the motion. The height, the maximum height it can go is at this point. We finally get a 0 up there, and initial v0. Using an equation involving v0, v, and g, and h, I can find h maximum height it can go up. This equation would give me height at any point if I know initial and final velocities. And by using the fact that final velocity is 0 there, I can find h maximum. Derive, again, a simple equation for h maximum. So let's put this equation first. V squared is equal to v0 squared minus 2g. H will be h maximum at half point. And again, this final velocity is 0 there. I'll end up finding v0 squared is equal to 2gh maximum, from where I can derive h maximum is equal to v0 squared divided by 2g. Again, this equation is useful for giving me the value for h maximum if I only know the initial velocity of the motion. We solved the question in midterm review part involving this. So t time, total time can be found if you only know v0 in this motion, and h maximum can be found if you know only v0 in this question. There could be some questions, maybe some further questions asking a velocity value at any point or height at any point, and all these can be used to find height at any point. Could be found using this equations or that, or if we are in the accelerating part, we can also use plus equations. So this is free fall. We'll also be solving some free fall, and all these equations are also on your formula sheet. And this is all we need to review about 1D kinematics. One last thing though, let me tell you that we might have some questions involving graphics. Let's review that as well. Graphical questions. It's quite simple. We might be asked about the direction of velocity and acceleration, values, and so on using graphical questions. So what we had was position versus time graph. Let's say meters and seconds. Units could be different as well. Be careful about units there and there when you're answering. And we had velocity versus time graph. So we meters per second and time second. If we are asked to find velocity using a position versus time graph, let me draw a not very simple graph in here. Let's say we have x in there, time in here, and we're asked to find the instantaneous velocity at one certain point. Let me call this t1 and x1. So if we're asked to find instantaneous velocity at these 2 points, what we do is draw a tangential line in here, and find the slope of this line, which will be tangent alpha, is equal to v instantaneous. If I want to put this into equation, it will be x1 over t1 at this certain point. But what we do, if we have a graphical point, we look at this and this value and find instantaneous velocity. And x1, t1 actually, to make it more correct, this should be the distance x1 and this should be the distance t1. What you have to find is these distances. So tangent is always opposite over adjacent, so the x1 over t1. If you are asked to find the average velocity in between 2 points, let's say t is equal to 0 to t in here, what you do is draw a line, let me use black for that, connecting these 2 points, and look at the angle you got there. Let me call this beta angle. And we average, we use v bar to find it, will be delta x over delta t equation, change in distance over change in time, and will also be tangent beta. Delta x over delta t will be, this is the change in distance, and this will be the change in time. So this is in terms of x, position versus time graph. Instantaneous acceleration found by drawing a certain, whatever the point they're asking us to draw a tangent line and find the slope of it. Average velocity would be asked in between 2 points. We connect these 2 points and look at the tangent line to find the average velocity. Same goes for velocity versus time graph, except now we will be finding instantaneous acceleration and average acceleration. Let me show you a different type of graph in here. Let's draw this type of graph. So if I'm asked to find instantaneous acceleration here at this point, I draw a tangent line in here, find tangent alpha is equal to a instantaneous, let me put in here, oh yeah, I did that too. So we find the tangent alpha the same, find the opposite over adjacent to find tangent alpha. It is possible to find from a graph. I'll solve some simple examples to show you that. I'll also make sure that we will have some questions on learning catalyst sessions on Monday and Wednesday. If we are asked about average acceleration, these 2 points, let's say t is equal to 0 to time t, and this is v here, we connect these 2 points. Again, look at the angle, let me call this beta again, And tangent beta will be a average, and it will be again change in velocity divided by change in time. So instantaneous and average velocity can be found using x versus t graph. Instantaneous and average acceleration can be found using v versus t graph. And let me ask you one question with one of these to see how we solved one in midterm review already. We solved how the velocity would be changing, increasing, decreasing, or would be positive or negative. We look at the tangent line, right? Let me remind you that as well. Let's say this is our x versus t graph, and we're looking at how the velocity is changing on it. Is it positive or negative? And if it is increasing or decreasing, we look at the tangent lines. Let me draw the same thing. We draw several tangent lines, follow up along from t is equal 0 to some time t, and see how the slope is changing. If slope is increasing, velocity is also increasing. If slope is decreasing, velocity is also decreasing. Let me draw two tangential lines and look at the slopes. Let's see, I have one in here, and this is the second one, 1, 2, let me call these. First line is less steep than the second line, so the slope is increasing. It means velocity is also increasing. Is the slope positive? Yes. If the tangent line is looking upward, it's positive. And here, let me give you one more example. Let's say this is also this is v versus t graph, so velocity versus time graph. And we are looking at acceleration. Let me draw the same graph as well. Let's actually make something more complicated. And let's look at the acceleration, how the acceleration changed in all these three regions, right? We had a question very similar to that. So 1, 2, 3. So I draw my tangent lines first. Let me draw two tangent lines in each section. So here I have upward looking, I put my arm parallel, upward looking tangent lines. It is positive, A is positive. And tangent line steepness is decreasing, so A is decreasing there. In the second part, second section, first line, second line, still positive, but now it is increasing because steepness is increasing. So here A is still positive, but not decreasing, increasing. And if I draw a tangent line in here, A is constant, steepness is not changing along the third section, and it is 0 because my tangent line is parallel to horizontal axis. So A here is equal to 0 and constant. So that is it. Let me solve another example. These are all examples actually, remembering from midterm review. Let me solve an example that involves some values. Let's use a velocity versus time graph. Meters per second times second. And I'm drawing my graph. Let's make it different. I have that. Second. And third section. Let's have one negative section as well. I gave you the answer already. Let's say it's going down like this. And I have times increasing 2, 4, 6, 8 seconds. And I have velocities 5 and 10, let's say. And I'm calling these sections again 1, 2, 3, 4. And I'm asking you to find the velocities in each section as values, average velocities in each section. So what is the average in each section? Let's call them V1, 2, 3, and 4. First of all, let's talk about if they are positive and negative. I might be asking you the directions as well, or might not, depending on the question, read the question as well. And I might also ask if they are decreasing, increasing, or constant. Now, I'm not going to answer this in here, I'm just asking you the average velocities. what you do, the velocity is changing here. If I draw slopes in here, different slopes, steepness increasing, velocity here is positive and increasing. Here, if I draw different slope lines, they will all be the same. It's all one line, one slope, so its velocity here is constant. And is it positive? Yes, still positive, but constant, not changing. Here, velocity is 0. Let me call this actually V2 again. V3, it should be 3, using 3. V3 will be 0. We don't even have to calculate because if I look at the slope, it's parallel to the horizontal axis. No calculations will be needed there. And V4 is constant. The tangent lines will not be changing, but it is negative. The slope is downward. So V4 is negative and constant. So positive increasing, positive constant, 0, negative constant. This could be a very nice question talking about how the velocity is changing, if it is positive or negative. Let's now find the values. Let's find V1, average value. So we'll be looking at connecting the initial line and the final point, initial and final points in the region where we're looking for the velocity. This will be our line in here, and this will be our alpha, and we're going to find tangent alpha. Tangent alpha here is equal to V1. How do we find tangent alpha? We look at this distance over here, opposite, and this distance over there, adjacent. Now we know this one, this is second 2, and we know this one as well from here, this is 5. So this distance, opposite distance is 5. This is also review for tangent, and this distance is 2. 2 seconds, of course, and this is 5 meters per second. If we divide, we'll get acceleration as meters per second squared. Oh, sorry. We can't ask me in here, I'm sorry, this is acceleration. Oh, please forgive me. Not velocity. This is velocity versus time graph. So these should be accelerations. Let me go back and review. I thought I forgot about the velocity. I thought this was x versus time graph. But no, sorry about that. V versus time graph. So what can we find from here is the acceleration. Everything else is the same. Only instead of velocity we have actual acceleration. Again, sorry about that. So this is A2, constant and positive, still same. A3, 0, and this is A4, negative and constant. Here we have change in acceleration. It's increasing and positive, still the same. Now let's find A1. It's still tangent alpha, only the graph is V versus T, so we can find average accelerations. And let's now find A1. Average A1 will be, again, this distance opposite, 5 meters per second divided by this distance adjacent, 2 seconds. So it will be 2.5 meters per second squared. This is our A1. Again, we had a slope line. We find tangent alpha. To find that, we look at this distance, which was equal to 5 meters per second. And we look at this distance, which was equal to 2 seconds. Opposite over adjacent is tangent alpha. So 5 meters per second divided by 2 seconds gives us our acceleration, average acceleration. In the second part, we do the same, but now our angle is different, or maybe not even different. Let's see. A is constant, but let's look at this angle. Let's call this beta, and we'll again find tangent beta. So we will say A2 is equal to tangent beta. Let me show that as well. This was equal to tangent alpha. And if I look at opposite again, what I have is the distance between 5 to 10 meters per second squared. So it's still 5 meters per second squared. And here, this distance is 2 to 4, so it's still 2 seconds. So we have the same actually. A2 is equal to still 5 meters per second divided by 2 seconds. 2.5 meters per second squared. They are the same. What is the difference though? They look quite different here, right? The graph is different. How come average accelerations are the same? Average accelerations are the same, but average the spontaneous acceleration is changing here, increasing as the time passes. Here it is constant. A3 we said is 0 because we have a parallel slope line and slope will be 0. Let's look at A4. It will also be the same. Here we have 5. So this will be, let me call this gamma angle. I'll use blue here, we already have something red. And A4 will be, take this here, A4 average will be tangent gamma. And if I look at gamma, opposite is still 5, adjacent is still 2, so it will be also 5 over 2. 5 meters per second over 2 seconds, so 2.5 meters per second squared. This is negative though, slope is downward, and it is also constant. And that's what kind of questions we could have. Accelerations in each region will not have the same magnitude always. Depends on the question. So we can now move on from here. One more thing we learned, we do so many questions, but if we have a velocity versus time graph, let me also remind you that if we have a velocity versus time graph, we said the slope of a line gives us the instantaneous or average acceleration. The area under the graph, let me draw a straight line graph so it will be easy for us to see. Let's say this is 5 meters per second again, this is 2 and 4, and we have this type of a graph. So velocity is constant in here, increasing in here and constant in there. The area under the line, velocity versus time graph, this area is equal to position in meters or distance traveled from initial point. So if we know the values, we can actually calculate it. We have here a square, 2 times 5, this would be equal to 10 meters, and this is the half of 10, 5 meters. So total distance traveled will be 15 meters if we have this as a question. And I believe this is all about 1D kinematics. Let's move on to 2D kinematics, and it's been some time already, so I have to just review quickly and finish this lecture. All right, so 2D kinematics. 2D kinematics could also have different types of motions. It involves X, horizontal direction motion, and Y, vertical direction motion. It could be we throw something upward, the way we do in soccer, or football, or handball, and volleyball is all involved in this motion. Or we throw something vertically straight, and then it will fall down like this. So it could, the most general form of it could be that we throw something from the floor, from the ground, with an initial velocity v0, with an alpha with the horizontal. It will go up to a point, come back down. As it comes back down, it will hit the floor again with the same initial velocity, same angle with the horizontal. This is important. This is also a symmetric motion. So the time it takes for reaching the h maximum height, is called t half. Will be equal to the second part of the motion, also t half. We will have a t total is equal to 2 times t half. And we'll have a maximum distance we can travel, what we call x maximum. We can also find the height traveled at any point of time. For example, at this point, if we know some values, we can find this height and this distance traveled along x-axis. And along x-axis, the velocity that does the job here is the initial component of initial velocity, x component of initial velocity, v0x. Let me put this x down here. And along vertical, the velocity that does the job is the y component of initial velocity, v0y. So generally what values we know is x component of v0 v0, which is v0x, and it's equal to v0 cosine alpha, alpha being the angle, initial velocity makes it horizontal axis. This is important. And y component of v0 is v0y, v0 sine alpha, the same angle. And we divide this motion into two. Along the vertical, what happens actually is exactly the same as the free fall motion, going up to a point and coming back down. Only now, instead of v0, we have v0y. In v0y, vy will be 0 at the highest point it can travel. The highest point it can reach is also called h maximum, the same. It will come back down with the same v0y. This is the vertical motion of this vertical part, let me say. And the gravitational acceleration is the reason for this motion. So we will have g. Slowing down, speeding up, and t half. T half is also the same, symmetry is also the same. If you look at any position in here, let's say the velocity becomes v in here, at the same height on the other side, velocity will also be v, and in the opposite direction. Initial v0x never changes. Along horizontal we have 0 acceleration. So v0x is always v0x, never changes. But since v0y changes along the motion, v will be changing. Only v0x will be constant. So along horizontal part is quite simple. It's a constant velocity motion. We have v0x, I can draw this a bit. v0x traveling along a horizontal line, and it travels a distance x at any point of time. Let me call this x in here. And in total time, it travels a distance called x maximum. And for this distance, the time passes is equal to t total. T total is equal to 2 times t half as well. Here it is the same. This t total is the same as this t total. The same motion. We are only analyzing it by looking at two parts separately to understand it better. And we here have the t half again, and t total is equal to t half. Now, along the horizontal, we have a very simple motion. Let me give the equations for horizontal motion first. So horizontal part. We have a constant velocity over and over again. I'm telling this v0x does this motion. It is constant. Acceleration is 0. So we have this. Any point of time at time t, x is equal to v0x times t. So distance traveled along horizontal. Horizontal distance at any moment of time, at time t. If I look at the whole motion, only difference will be the time passed. T will be equal to t total. And the distance traveled along horizontal will be x maximum. Using that fact, I can find x maximum, which is equal to v0x times t total, right? So if I know t total, v0x, I can find the maximum horizontal distance that can be traveled by a motion. So maximum x, let me call that to be short. This is horizontal motion. Vertical motion is exactly the same as free fall. Only now instead of v0, we have v0y. We have y component because we have another component of motion now, and that is all. So let's write down free fall equations involving v0y and vy instead of v0 and v. So v0 is replaced by vy now. Replace. And v is replaced by vy. So v0 instead of v0, we will have v0y. Instead of v, we'll have vy. And all the equations will be used in here. So vy at any point will be v0y minus gt If I'm looking at this part of motion, if this part of motion would be plus gt, let's put the plus actually. And if the object is decelerating, again we'll replace plus with minus. I'm not going to show it in here. Or should I? I can maybe put them in here. Let's see. And we will have vy squared at any point will be v0y squared plus 2gh. And we will have h at any point, height threshold at any point of time will be v0y times time plus 1 over 2gt squared. Now this is again for accelerating part of motion. Accelerating. And for decelerating, let me also write them. You will replace plus with minus. I didn't include the minus part in your formula sheet, but I put a note that if the object is decelerating, acceleration will have negative direction and all the positive will be turned to negative for the terms involving acceleration. Let me show this to you again. We will have Vy is equal to V0y minus gt. The acceleration portion of motion is from initial position to highest maximum position. And after that we have acceleration. And we can use Vy squared is equal to V0y squared minus 2gh. And h is equal to V0yt minus 1 over 2gt squared. X motion, constant velocity, y motion, free fall, decelerating, accelerating, symmetric motion. So we'll have t half, t total is equal to 2t half. And the useful equations for h maximum and t total is also used in here. Again, we only replace v0 by v0y. And let me also show you useful equations for this motion. I'm going to delete these and show them in here. You will also have these useful equations in the formula sheet. Let me quickly check if I remember to include them in the 2D kinematics part. Yes, I did. So we had for free fall, let me remind you again, that t total is equal to 2v0 over g, and h maximum is equal to v0 squared over 2g, using the fact that the objects will be decelerating, having a zero velocity in here, which will be y, will be 0 in here, and the maximum height will be traveled, t half will be traveled. We derive for t half and h maximum, and t total is equal to 2 times t half. This is where they are coming from. So this was for free fall. For the 2D motion, we replace again v0 by v0y. The same equations will be used. So we will have t total is equal to 2 times v0y over g, and h maximum is equal to v0y squared over g. And there you go, your equation, useful equations. One more useful equation we can derive from here, let me see if I also show you that, yes, is to enter this t total in here. So x maximum, if you see we have x maximum, maximum horizontal distance that the object will travel within the whole motion is v0x times t total. So we can enter this t total value we obtain in terms of v0y to get another useful equation. We can directly use that equation as well. And I'm looking to see where I can put that. Let me delete this part, the accelerating part, and put it in here. So I am entering this t total in here and deriving another equation for x maximum, which will be x maximum is equal to v0x. Instead of t total, I am putting 2v0y over g. G. This could be another useful equation. This will be another useful equation you have in your formula sheet that you can use. And that's pretty much it. We'll be solving some questions involving this on Monday and Wednesday, hopefully. And that's the end of this lecture. See you on Monday.